Right. No, I don't. It should also like that. Yeah. It should work. It goes forward. Should. Absolutely. So does it go forward or? Yeah. Okay, good. So welcome everyone again. This time we are lucky enough to be hearing Dimitrios Psatis talking about harnessing AI and ML techniques for compact object astrophysics. Apparently, he's from Georgia Tech. I don't need to introduce. We've been here. So thank you very much one more time. Go ahead.
Thank you very much, and thank you everybody for coming to my presentation today. I was here 20 years ago, almost to the day. I think everybody mentioned that before. Ali Alpar organized a series of lectures in Karaköy in June of 2004. And Feryal and I were assistant professors at the time. We were starting a new direction. Feryal was measuring neutron star radii. I was doing tests of general relativity. And we thought, I think Yavuz was there in those lectures as well. Definitely a very, very young little graduate student was there, beginning graduate student. And Tolga impressed us so much that he actually, as Feryal said, he came to Arizona, became a student, became a postdoc. He had done amazing work. And I'm really happy to be here today, 20 years later, because I am starting a slightly different direction, which, as the title says, and as Tolga mentioned, who knows why, about harnessing AI, artificial intelligence, and machine learning tools in compact object astrophysics. And if any of your students who are thinking about the future are interested, by all means, come talk to us afterwards, and we'll be more than happy to chat. So why do we go that way other than it's fashion, right? Everybody's doing that right now, but why do we think we're going to learn something that we didn't know before? And when people talk about AI and try to motivate the use of those kinds of tools, they usually talk about the enormous amount of data that we're going to get in astrophysics in the next decade or two. If you care about black holes, especially things like supermassive black holes and how they grow through cosmic times, then we have JWST that is going to start observing the seeds, the very first black holes in the beginning of the universe. We have surveys like the Zwicky Transit Factory and Rubin that are going to be observing every day hundreds of millions of black holes. This is an insane amount of data. We have ALMA, the VLA, new generation VLA radio telescopes that will be taking more detailed observations of the nearby regions around the black holes. But more importantly, we will be looking at black holes with other messengers like neutrinos, with IceCube that is already happening, nanograv and light gravitational waves, and of course X-rays and so on and so forth that I'm not including here. And all these telescopes are going to be coming online, have been online, and will be coming online in the next few years, and they're generating data at an insane rate. Right? The Rubin itself will be generating 7 petabytes of data per year. And as I said, hundreds of millions of black holes observed every single day. And somehow, there's not that many people working on that field, we will need all the help that we can in order to be able to look into that data, analyze that data, and get the most out of it. Now, in the Event Horizon Telescope, we're not unfamiliar with this kind of data rates. And as Feryal mentioned, this is the Event Horizon Telescope. And I would say that when we see 7 petabytes per year, we're like, yeah, whatever, we will change, because we were collecting a petabyte of data every single day of observation. The Event Horizon Telescope has the largest collecting rate of data of any experiment in the history of physics. And somehow we have to take this petabyte of data every single day and turn them into images. And I was not going to talk about that because I thought I will talk about that. But we actually even used some machine learning algorithms to improve the original images of the M87 galaxy into something with much better resolution, keeping all the limits of the event. But this is not what I'm going to talk about today. Okay. I don't want to talk about how AI and ML algorithms are going to help us in analyzing vast amounts of data. Instead, I want to talk about how AI and ML methods will help us make much better theoretical simulations, and more importantly, perhaps learn new physics. Okay, because that's something that we don't hear a lot. And the main issue, again, Hayal showed that slide, is that everything in the universe, especially things like black holes, happen at many different scales, and every scale interacts with every other scale. Starting from cosmological scales, galaxies, which is what provides the matter that fits into the supermassive black holes, the factor of 1,000 from here to here. From the outer regions of where the black holes fit into the inner regions of that accretion flow, the accretion disk that we're trying to image, another factor of 1,000 all the way to the event horizon, and a factor of 1,000,000 further down, or a factor of 10 to 1,000,000, all the way down to the microphysics of plasma where physics actually happens, right? And there is no way in a modern computer algorithm to simulate everything. People, as you see in the background, there's a simulation of structure formation that generates perhaps galaxies. We can simulate accretion flows by themselves. We can simulate what happens very close to the event horizon, the kind of things that Peral was showing. We can make plasma simulations for the microphysics, but we only see piecewise what we're trying to learn. We're only doing this simulation, only that simulation, only that simulation, and we have no way of connecting everything into a big simulation of all the scales of matter. Right? And this has been a fundamental problem for a very long time. So how do we solve that problem? Well, this is the part where in my lifetime I was very lucky, but for all the students here in your lifetime, you're really less lucky. Wait, yes.
Excuse me, that picture is imagination or?
Let's call it theoretical simulation. It's theoretical simulation of magnetic fields. These are different cross sections. Yeah, you put that magnetic fields in the active. So imagination, realistic imagination. So why do I say that I was very lucky in my lifetime, and all the young people here are not going to be as lucky? I'm sorry, these people over there. Can you see? Yeah. Okay, thank you. The reason why I say that is this graph. And this is the part of the graph that we've seen before. What I like about this graph is it's my lifetime. I was born in 1970, right? So this is how fast, how bigger, I shouldn't say fast, how bigger computers have become during my lifetime. And this particular graph, this is in years from 1970 to 2015 when they stopped collecting the data for this particular graph, shows the number of transistors, like junctions, that one can fit in a single processor. And this is in thousands. So this is 1,000, this is 1,000,000, this is 1,000,000,000, this is 10 billion. And this is nothing but what we call now Moore's law, right? That every about a year and a half, we double the amount of transistors that we put in every infinite chip. So what that means is that when I was a graduate student in 1992, if I wanted to do a bigger and better simulation, I just had to wait for a few years, right? And then, by the time we finish the simulations, computers got better, we got a bigger simulation, and this has never slowed down until now. By the way, there are different technologies that allow this to happen. It's not the same technology, but it has becoming more and more capable. The problem is that, as I will show in a second, how many transistors you put in a computer does not translate with how big problems you can solve, or more importantly, how efficiently you can solve them. And the reason is that there are other things that you need to look around. And the one that I am pointing more importantly is the performance, how fast the computers become. And you see, originally, up until about 2005, the performance of computers was parallel to the number of transistors. But after 2005, the performance of computers has dropped by a factor of 50 to 100. The computer that you buy today on a single core is by a factor of 50 or 100 slower than the computer that Tolga bought when he was a graduate student. Okay, so the reason that you're slower, you can tell from your computer, nothing else. So why did this happen? Of course, the number of cores, the number of parallel cores that you can put in a particular computer increases very rapidly, like that's what GPUs are. But why are computers slower and slower and slower? Now, you never thought that you will come back to talk about electronics. Remember electronics? Second year, whatever, third year undergraduate. So the power that you need in order to drive a computer is proportional to what's called the load capacity, the voltage squared, the frequency, the clock frequency, how fast you do the calculation, and the number of bits that we bring simultaneously, 8 bits, 10 bits, 13 bits, and so on. And the voltage is current times resistance. And if you remember, resistance is coefficient length divided by surface area. As you make the transistor smaller and smaller and smaller and smaller to fit more and more and more and more, because that's what the computer industry likes to do, the surface area wins. This is difference square versus that. The resistance increases dramatically. The voltage scales as resistance. The power scales as voltage square. So you will need twice as much or about square as much power in order to drive the same performance. And the power is flattened because we don't want to be using more than about 150 watts in the computer. And what do you do for that? You drop the frequency of the calculations. So the frequency in megahertz, the rate with the clock in your computer has to be significantly reduced in order to be able to put so many transistors in one single signal. That's why your computer is slower. Quantum computing will help. Quantum computing will definitely help when it works. The difference with quantum computing is that there's a number of calculations like interference or cryptography that quantum computing can do really, really well, but quantum computing was never designed to solve general computing problems. Right? So, well, of course, works better, you're going to say, but even though per calculation I'm slower, I can have significantly number of parallel calculations, right? And therefore I can do significantly faster parallel computing. The problem with trying to do something over hundreds or thousands of parallel cores is that you have to communicate the data between all of those cores, and that significantly reduces the efficiency of your algorithm. And there was a recent very nice study about a particular benchmark with a number of different GPU and CPU algorithms that shows what the fraction of the peak performance of the computer those algorithms achieved, parallel algorithms. And it's between 0 and 3%. So yes, using hundreds and thousands of computer cores to solve that problem, in principle, you can get that increase, but the more cores you use, the less efficiency you have, because now you're wasting all your time communicating data. In other words, our performance with the kind of code that we do, not for trivially parallelizable algorithms, like, for example, cryptocurrency, that's a trivial parallelizable algorithm. One core doesn't need to know what the other core is doing, right? For the kind of simulations that we do that require a lot of discussion, conversation between the individual cores, then effectively our computers stop becoming any better in 2005. Okay, that's why I said I was lucky, you are not. However, what that means is that we need to find another way to start solving bigger and bigger and bigger problems. And that other way has to be algorithmic. And this is where AI and machine learning becomes important, because hopefully it's something that will allow us to go to harness all this power in a way that waiting for the next bigger computer will not allow us. I'll stop for a minute for questions. I think much. Okay. So when we say AI or machine learning, we mean many things, right? Not everything is the same. And this is a nice graph about a year ago that puts what we call AI into originally 3 big types of algorithms. Something that we call unsupervised learning. This is when you don't have to tell the algorithm what is right and what is wrong. It just does things for you. And obviously things like clustering or dimensionality reduction, you don't have to say what is right or wrong. I give you a graph and the computer says these are clustered together. Just figures out by itself. There's algorithms that are called supervised learning, where we train the algorithm, give it input and say, this is right, input, this is wrong, and we supervise the learning. And classification and regression, forecasting, and so on and so forth are what's called supervised learning. We have algorithms that are called reinforcement learning, where the computer itself plays the game multiple times and learns what is right and what is wrong. So for example, if we have a computer algorithm to learn chess, it can play 100 million games of chess and figure out who wins again. We don't have to tell it what it is. It's reinforced. And what has happened, of course, the last couple of years is something that encompasses all of those, that we call either deep learning or generative AI, where effectively you write a very, very, very generic algorithm that does what never needs, right? It's going to cluster if it wants to cluster. It's going to figure out from what you give it. It's going to play games by itself. It's going to give it. It's going to do whatever it takes. It's so big a model that it actually does whatever needs to be done. So these are the kind of tools that we have right now in our hand, and hopefully, as I will show in a second, there's more tools that are more specific to physics problems that are not, the rest of the computer industry doesn't care that much about. And we hope to use them to progress them, especially compact objects such as astrophysics in the future. But we also need to be a little careful when we're using AI techniques, because contrary to a lot of the other techniques that we've used before, computational methods for solving equations and so on, AI algorithms become exceedingly more complex, and I will say something about that. We'll show something about that in a second. And if we don't understand what we're doing, if we don't understand why the AI algorithm gives a particular prediction, then we are bound to make mistakes and think we got the right answer. That generically is called hallucination. The algorithms hallucinate, right? They just think things happen even though they're not real. And when it comes to science, whenever somebody tells you a result, you always ask, where did it come from, right? You need to be able to give attribution of result, like where did the number come from? To ask, why did this person make that decision? And to give you an idea of, this is a very famous example by Lapuskin a few years back, of how AI algorithms can confuse themselves and give some wrong answers. This is not physics, a very simple situation where they trained an algorithm to identify horses from images. So you give it an image and it tells you horse, not horse, right? Clearly. But then this was something that was known for a few years how to do it. But then this particular people developed an algorithm to point out where in here, what part of the image did the computer algorithm think that made it into a horse. Right? And if I told you, you would probably say 4 legs, something that looks like that, ears, whatever sort of tail, it's not a donkey, whatever. So they asked the computer to identify what pixels did it pick to say that it was a horse. You know what it found? I kind of blocked the print here for a second. It turns out that the images that they gave to the computer to train what's a horse or not horse, all the horses were taken by a particular photographer who loved to put his signature at the bottom of the figure. And when they asked the computer to say, how do you know it's a horse? It says because of this. Not because of the horse, but because it was the signature of the photographer who took all the horse pictures that they put to train the model. So they removed that horse signature and suddenly became no horse. So they took the car, they added the signature and suddenly it became a horse. Right? So the algorithm was trained in something that to our eyes was obvious that that's not what the horse is, but we cannot teach the algorithm what we really think we're teaching the algorithm when we just make it an unsupervised, actually that was supervised decision, we call it horse, but we didn't say why, right? And the algorithm hooked onto what was always there when there was a horse, because the horses, of course, some horses were pointing this way, some horses were pointing that way. There was white horses, there were brown horses, horses from above, horses from below, but that always stayed for horses. So the algorithm thought that's a horse, right? So this is something when we do physics that we cannot do. And by the way, there's a beautiful New Yorker cover page a few months ago that pointed out exactly the same point. So here's an author, writer, right, who's trying to write an article for New York and cannot do it, and scratching all the papers. The robot goes there and says, I can help you. And this is what he did. Because by looking at it, he thought that that would be exercise to take the papers and make them into scrancing as opposed to, actually write the piece of work that they need to do. So this is the kind of thing that we don't need to do. You can easily see, especially in astrophysics, if you're going to give it a lot of images to understand something, it says the black hole is the neutron star, is the big black hole, is the small black hole, is the shadow, is not the shadow. You need to know what it's looking into. But the other thing is something that we call knowledge transfer and generalization. And this is another example. Toyota, the car company, built that robot that was shooting free throws from all different directions. This is a time-lapse sequence of that. And this was reinforcement learning. So it shot it didn't go in, it shot it again, it went into changing parameters and so on. It got to a point that it had a 100% success rate, right? Because it figured out exactly what was the proper way to shoot it every single time. And of course, it's fully reproducible. And they never told it the equations of physics, but it figured out if I do from this point to that direction, in this spin and so on, it will come in, and I will always keep it doing it, right? Because it can reproduce. I mean, this is a trivial calculation, it's a fitting formula, as I will show in a second, right? What do you need the input to be for the output to be a particular way? But did the robot learn physics? Not really, right? Because how can I use now this algorithm and generalize it or transfer the knowledge to predict the motion of a rocket in space? I cannot. Right? There's nothing that I can use this algorithm for and then put it in a rocket, press the button, and the rocket does wherever it goes, because it didn't really learn physics, it didn't generalize the knowledge. It just learned input, output, input, output. And again, this is something that we do not want our AI ML algorithms to do. In a lot of things in everyday life, like shooting basketballs, maybe that's all that people care about. But in physics, we want to be able to generalize into something. So this is our goal. And to give you an idea of the directions that we're going to go, as I said, I'm not going to talk about the image reconstruction for the black hole. I'm going to talk about two other things. One is straightforward and simple. It's a very simple neural net, and just want to give you an idea of simple things that we can do. The second one is a more dangerous algorithm that I'm going to spend a little more time towards the end. So what's one example of how we can use ML in physics? Well, interstellar, how black holes are not supposed to look like. Like you were really upset when they came up with that because, this sometimes earlier, this is how black holes were supposed to look like, but they didn't because they did the wrong physics problem, solved the wrong physics problem, but it doesn't matter. There was a Wired magazine, I have it here, article about interstellar and how they tried to make it as realistic as possible. And they said that because of the gravitational lensing, it was so taxing that some individual frames took up to 100 hours to render, the computation overtaxed by the bending bits of distortion caused by Einstein's effect, so gravitational lens. In other words, if you want to figure out what a black hole looks like, as we all pointed out, you need to trace the photons from where they come from, and that to do that tracing requires solving Einstein's geodesic equations, which is extremely slow. Those people were not very smart. It took them hundreds of hours. At the same time, we had actually, well, I can show that in a second. I will come to that in a second. At the same time, we had done a lot more efficient algorithms. I will show in a second. It will take us a few seconds to do it as opposed to 100 hours, but even that is extremely slow for what we want to do. And this is the kind of gravitational lesson we're talking about, looking at the black hole from above, sending photons towards the black hole at different impact parameters. And you see, depending on the impact parameter, you get some significant amount. This is what happens when you have a black hole, but it's not that different when you have a neutron star, because a neutron star is just about the black hole, like 2.5 times as large as the horizon of the black hole, give or take. And therefore, photons near the neutron star experience significant amount of gravitational. And this is the problem that we really care to solve about, the neutron star one, not the black hole one right now. Because if I have emission from the neutron star itself, so this is a numerical simulation of the emission from polar caps, particles coming back towards the neutron star and emitting X-rays, as the polar caps rotate in and out of line of sight, gravitational lensing allows you to see behind the neutron star. And the amount of pulsations you observe depends on the gravity of the neutron star. Right? If the gravity was so strong that it would float the way around, then the pulsation would have gone away. I always see the spot. But for less and less amount of gravity, larger radii or smaller mass of Newton's star, you get the gravitational potential. And this is something that is not an intellectual curiosity anymore. Nicer, the X-ray emission is actually attempting to measure radii of Newton's star using this method. So in order to be able to compare theoretical predictions of hotspots moving around like that to the simulations and do all the statistics, we need to be able to do that calculation extremely fast, much faster, not 100 hours per image. I mean, that would have taken, months to do that simulation, but significantly faster. And as I said, back when, in 2013, we had, when we were working on similar problems, we had attempted to use GPU cards. It was very early on to use the graphics processing units cards that everybody's using right now. And as a function of the number of rays that we were calculating, what that was, this is the million rays, right? This is a good size of the image of 10 to the 5 rays. This was the algorithm that was using normal CPUs and will take about 10 seconds. This was actually an analytic calculation. It was slightly better, but not that much. And this is the GPU that we'll get in about a second, factor 50 to 100 improvement by using GPU technology. But even that, for each one of those images, to take a second to calculate what that image looks like, different phases of the Newton star, and then do the full Markov chain Monte Carlo with all the statistics to fit to the data, where you need tens of millions of those, this is really impossible to do, right? Is there a way that a machine learning algorithm allows us to do that calculation significantly faster, which is not that different than the basketball, right? The basketball allows you to solve the trajectory of the basketball. Here we want to solve the trajectory of the photon interpretation. So this is our geometry. This is your neutron star. You observe it, the screen of the observer far away. The neutron star is spinning at some spin frequency. It has a mass and radius. We observe at some inclination, and there is a spot on the neutron star at some polar angle and at some azimuth. What is the flux that I observe here? It's just a function, right? Function of mass, radius, spin frequency, inclination, and location of this frequency. So in principle, the only thing that I need is fitting, is a curve fit. Can I find an approximation to this function that approximates the result of that complex calculation? If it was a simple function, we could have guessed it, something like that. But this is clearly a very complex function. So what do? This is where simple neural networks come in, right? I say these are my input parameters, and I want to fit a function that spits out flux. That's the goal. Let me suggest one. This is a function. 1 over 1 plus e to the minus a weighted sum of all the parameters plus a number, right? I say maybe this is a good function. I'm going to say this is silly, that's not a good function, because when I plot this, it's a sigmoid, right? It goes from 0 to 1. Now, this is a very silly function that is activated. It goes from 0 to 1, it's like a bit, when the sum of the model parameters, weighted model parameters, crosses the thing. And by the way, the reason that this was put out there is because this is how people model a single neuron in the brain, right? The idea is that you have different inputs, and if those inputs cross a threshold, then the neuron is activated and sends a signal on the other end. That's why this function is called an activation function, and whatever this is the weights and divides. But this will never be a good function, one of them, to solve everything. So how do I build more complicated function out of a single neuron? By just combining. So these are again my inputs. All those inputs fit this neuron, that neuron, that neuron, that neuron, the first layer with different weights. All of those neurons fit the next layer with different weights. All of those neurons fit the next layer with different weights. And at the end, I combine everything with a slightly different function and make the flux. So I made effectively a very complex fitting formula, which is a sum of a lot of those activation functions with weights and biases that I don't know a priori. And I ask myself, if I give here the input parameters and give here the output of each and every one of combinations that I can imagine that I solve with my complex problem, is there a set of parameters combinations that can always fit? It's a very complex fitting problem. And what you write is this is a chi-square. How different is the prediction based on the best fit parameters as a function of how many neurons you have per layer? We call it the width of the neural network, and how many layers you have. And you see that the minute you start putting 3, 4 of those intermediate layers, the predictions become better and better and better the more neurons you see. This is what we call a learning curve. And this is what tells you how well you've done. The chi-square is about 1 part in a million, which means that the average difference between the prediction and the truth will be 1 part in 1,000 square root. So a neural network is nothing but a non-linear complex fitting formula. And why does it work? Why could we not do it 5 years ago? Well, part of the reason is that even though this seems like a very small number of neurons, if you ask how many free parameters does that fitting function have, all the weights and all the biases, it has about 500,000 free parameters, right? So I wouldn't, if I ask you, are you surprised that that simple neural network fits the result of all my simulations? Think about if I told you that I made a fitting function that has 500,000 free parameters and I fit the results of the simulation, would you be surprised? No, right? It would be like, probably there are too many, right? But we're doing that 1 part in a million. And this is the whole point, that how do I find those optimal 500,000 parameters? If you ever try to do a fitting, the minute you have more than 20 or 30 free parameters, it's very complex. It turns out that if you're using those activation functions that I told you, those sigmoids, there's a very efficient algorithm for backpropagation that computer scientists have developed to train neural networks that allow you to train hundreds of millions, hundreds of billions of parameters. Extremely efficient. So there's nothing fundamentally different in our understanding. The difference is in the computational method. And I can then show you, so pick the number of parameters, mass, spin frequency, inclination of the observer of the spot. I change the phase of the spot on the Newton star. The dots are the extremely complex calculations from the ray tracing simulations. The line is the prediction of that, the fitting formula from that neural network. And this is the residual, which is better than the percent. This is 9%. So I effectively trained a neural net, which is the same as saying I came up with an extremely complex 500,000 parameter fitting function to reproduce the results of all my numerical simulations. So now I never have to run a numerical simulation ever. And if you ask yourself, how fast is evaluate that neural net now? Well, this is what I showed you before. For a 512 by 512 image, which is about 2 times 10 to the 5 rays, the neural net takes about 5.4 milliseconds. This is this is a millisecond, I put it here. I don't know why that moved. It's about here, so you get another factor of 100, even based on the CPU calculation. So this was a very simple neural net that we did and trained in order to be able to push forward something without waiting for the computers to become better and better. Any questions? Well, that begs, of course, this statement. And Jan LeCun is a professor in New York who is now the chief scientist at Meta. He's considered the father of deep learning. And this is something that he posted on Twitter, that is called X now, about what I showed you with not deep learning is actually a very shallow network. But he said deep learning is not as impressive as you might think. It's mere interpolation resulting from worldwide carefully, right? Which is exactly what I tried to demonstrate. Can we do any better? And this is where the generalization to different cases is. Just like with the basketball, what the robot did with the care fitting between the input parameters and the output, and always got the right input parameters to get the same output. But in learning physics, can we do it? Generalization. And what people usually Good. So what people usually talk about when they talk about the fundamental differences, think about in astrophysics the difference between Kepler and Newton, right? What did Kepler do? Kepler did a fitting formula, right? I mean, this is just one of them, but in the ellipse. Looked at all the data in the sky and said, I can draw an ellipse between them. Which is totally fine, it was great. But you wouldn't be able to use Kepler's law, if you didn't know what that M was, by itself, and apply it to a star around the black hole. Right? You wouldn't be able to do it in generalization. It was Newton who converted the fitting formula into a differential equation, dynamical model, that allowed you to generate that fitting formula, but also apply the same fitting formula to planets around other stars, stars around black holes, to galaxies, stars around galaxies, and so on. So what we really want to do is we don't want necessarily to do fitting formula, some of them are good, but not always. We want to convert the fitting formula into fundamental equations because this is what it's physics. Now, we were not there when Newton did it, so I don't know how he came up with his differential equation to fit Kepler's law, but we know how Einstein did it. And there's another beautiful way of doing it. Now, of course, this is the wrong equation, right? This is special relativity. But actually, Einstein reverse engineered the whole equation in general relativity. At some point in 1915, he and his friend Marcel Grossman said, we know that it's got to be a tensor equation. We know that one side has to involve gravity, the other side has to involve matter. We have no idea what the terms are. And then he did three different I have no idea what they're talking about. And then he wrote three papers over the course of the month, in which he tried different terms. He tried the first term, didn't work out, actually was not conserving energy. He tried the second term, it was conservative, but he couldn't explain the periastin precession of Mercury. And then he tried the third combination at the end, and that's how he came up with this theory. So fundamentally, what we want to do when we have data is we want to try, and maybe there's smarter ways, but the simplest brute force way is to try all possible differential terms that can describe that data and find which one works better. Now, it takes a second to realize that there's an infinite number of differential terms that explain the data, right? If I take a differential equation and differentiate it itself, then I'll get another differential equation that is as good for more terms, and then differentiate it again, and so on and so forth. So what we're trying to find is the smallest number of differential terms that when you solve that differential equation describes the data. And then as physicists will try to figure out what it means. But that's the second thing. We're still trying to understand the physics. And this is called model inference. And from the data, I derive what the fundamental differential equations that the data describe. And in the last 2 years, there's been a couple of attempts, starting with Cindy by the group at University of Washington, and then became a little more elegantly done with the presence of non-equidistant data using another method called Spider at Georgia Tech, where people came up with a fundamental brute force way of doing it. Now, I'm not going to give you the mathematics of it. I will tell you directly what our goal is, and I will try to describe that as an example as part of our goal, because otherwise it becomes too complex and abstract. So this is the goal that I started from the beginning, this big scale separation between things that happen at the scales where we can simulate accretion around black hole. So this is the size of the black hole. You know, for M87 is about 10 to the 16 centimeters. And the place where plasma processes happen, this is where heating and viscosity happens, which is at the scale where electrons and protons gyrate around the nucleus. This is a cycle. And there is a, 7 to 11, 12 orders of magnitude separation between the two. People do kinetic simulations. This is from Ferial's kinetic simulations in this regime. People do magnetohydrodynamic simulations in this regime, but nobody can simulate both. What we really want to do is we want to take the outcomes of the simulations of the small scales, describe them in terms of simple physical differential equations, what we call a closure scheme. I will say something in a second. Feed it into the big simulations, and then run the big simulations in a way that incorporates it. And to be a little more specific, we're going to be a couple of equations now, but hopefully that's all you're going to see. Equations of magnetohydrodynamics, densities, velocities, derivatives with respect to time, derivatives with respect to space, continuity, mass conservation, momentum conservation, pressure, magnetic forces, and the induction equation, the fact that as a plasma moves in magnetic field. This is the macroscopic equations. This is the equations that we solve in the big scales. But this is called ideal immediacy equations because we don't do the dissipation, the little turbulence and heating in this environment we cannot resolve. In principle, we want to add terms, viscosity and dissipation terms, that we can only more measure in the smallest scales. So we want to go to the small scales, measure those terms in terms of derivatives or whatever it is, and add them in this equation, and then make it run simulation and report it. So how would we do it? First, we need to run a large number of small simulations, all possible conditions. Then we take those big simulations, and then we take different volumes, a large number of volumes, samples. Like we sample those simulations because of course not everything happens all the time, all the simulations, right? You need to sample the simulation. This is an example of a particular problem. This is now time in one dimension in space. Think of it as it's a four-dimensional block, and we're picking boxes in those simulations. These are different samples of phenomena that would happen. There's a connection here, there was heating there was laminar flow there was expansion there was contraction there. We want to be able to sample all those things. And the goal is to find terms that involve macroscopic quantities, velocities and their derivatives, to describe what happens in those terms. So one slide that requires a bit of thinking. How do we do it? Here's an example. Suppose that I didn't know it, right? I did an experiment with magnetic fields and this and that, and I told you can derive the equation. You will need to derive this equation, right? This derivative is equal to that derivative, which I can move to the other side, and we need to derive this equation. What you see is this equation is a sum of terms that involve derivatives that they all add up to 0. From now on, we will call this a sentence. It's a sentence. Each term we're going to call a word. We're bringing terminology from AI now. Each term in the product, we're going to call it a letter. And the numbers in front, we're going to call them words. Right? Because what you see is that there's a small number of letters that I have, densities, velocities, magnetic fields, and pressures. But I can combine them in words of different lengths. If I consider the derivative one letter, this has 2 letters, this has 4 letters, this has 3 letters. I can combine them in words of different letters, different number of letters. And then when I make a sentence, adding up all those words with different coefficients, it should be up to 0. Right? This is the goal. And this is my alphabet. This is all the letters that I have. Velocities in 3 dimensions, magnetic fields in 3 dimensions, density, pressure, and derivatives. I choose how the largest word that I'm going to use, how many letters will it have. Right? NHD goes up to 4, but I want to go beyond NHD, so I should go 5, 6, 7, 8, 9, whatever. And I'm trying to find the minimum number of words in the sentence that if I add all those words, I get equal the sum equal to 0. This is my differential equation. That's the goal. And as I said, people have been trying that for a few years, but there's a very big bottleneck why it has not been applied. And we call this the library catastrophe. What is the total number of possible combinations, number of words that you can make when you have a given number of letters? Right? We have 12 letters. So if I want words that have one letter, I only have 12. 2, 3, 4, 5 letters. By the time I have 5 letters, I may stick as 4. But I have 5 letters, I'm in 10,000 possible terms combined. Not only do I have 10,000 different terms, I also need all the possible combinations of all of those possible terms to check things. Right? Remember, I'm doing Einstein equals ma squared equals mb squared equals mc squared. I'm trying to use all the possible combinations to figure out which ones describe, which is the smallest number of words that I have to describe the data. And I have to go to tens of thousands of those possible combinations and all combinations of those words to make all possible sentences. It turns out that this is an extremely, as you can imagine, time-consuming experiment. So what we did here, at some point was prediction. These are standard algorithms that existed. So this is the SINGI, and this is just exhaustive search. Sorry for the small things. This is word size, 4 letters, 5 letters, 6 letters, 7 letters, and so on. How long will it take to solve this problem with the MHD equations that I showed you? In seconds. This is a day. This is a year. This is the Hubble time. This is the age of the universe. This is the first time that I put the computational algorithm, compute time, and I include the Hubble time. I think it's to be an astronomer, right? And what you see is that by the time you put words that have 9 letters, 9 possible terms, kind of combinations, standard algorithms will take a good fraction of the age of the universe to run. Which, I don't know about you, I'm not waiting that long. If I live that long, I won't be doing this for the rest of my life. So we wanted, this was a proof of principle, but we didn't have the computational tools to solve it. AI, this is an AI to begin with, AI computer scientists to the rescue. There is a particular way, it's called gradient single binary decomposition, that we developed with completely different vision that we ported in this particular problem, this is an article problem. And we have a new algorithm that we call accelerated null vectors from bisection. It involves some bisection between some situations, and this plus algorithm. And this is the computational time of our algorithm. What used to take Hubble time, we can now solve in a year. And remember, you have to do it once, right? So that you have once per example, once per problem. So now we can, and this is on a single book, use tens if you use it becomes a month. So now we can take insane amounts of data, whether they're from simulations or from real data, and within a month, a month, be able to identify among the other examples, so hundreds of thousands of possible equations, differential equations, which are the simplest possible differential equations that describe the entire data. And this is what we call relevant physics, right? Because then we'll have to be able to interpret them and say what the steps are. But this is the first step to actually doing something generalized that then I can apply to a different plasma physics situation. I can apply to a different physical place as opposed to just a fitting formula. And for now, we've done it only in, as a proof of principle. We run simulations without assuming that they're data, without knowing that they're run by MHD simulations, and try to figure out how we reproduce the MHD equations. So this is a particular set of simulations. You cannot see our student's name here. That simulation is not there. And why the simulation is not running.
It's running.
It's running, that's hard to say. So this is a searing box simulation that the box is seared in this particular way. It forms what we call tunnel solutions for a little while. You can see them here, and then they break into three-dimensional turbulence and becomes a chaotic system. Right? We start with data from this chaos. So we give data that have to do like those little volumes with thousands of those from that chaotic system. And we say, can you tell me what are the differential equations that that system solves, obeys, in order to give rise to that mess? And the way that we plot it, so this is Rambo's equation, the continuity equation, we know that this is the correct answer. The way that we plot it, remember the sum of all those terms has to add up to 0. Right? This one has to be equal to 0. This is the relative contribution of various terms, 1 term, 2 terms, 3 terms. By the time you hit 4 terms, you practically hit the floor. This is the error in the way that we do the measure. And up to here, what are the terms that we add? 0.997 times the time derivative of density, plus practically 1 times this time derivative, plus 1, this is normalization, plus almost 1 times this derivative, which is practically the same equation that we started with coefficients that up to 1 part in 1,000 are the same as we expected. We didn't give it this equation. We said, out of 100,000 combinations, find what is the equation that that segment system obeys. It came up with that. And then we did the same for the momentum equation, because this has minus sign, it has a 1/2, and 1, 2, 3, 4, 5 terms, and then the floor. And what you say, 1, 1, 1, half minus 1 is equal to 0. So it serves through all possible combinations and identify what those equations are. So here we are. We have the tools. As I said, this has not been published yet. The algorithm has been published. We just developed the algorithm that allows us to do this in massive scale. Get knows SingPy and has experience with how to do it in a singular possible case. And we now are in the place where we're running those small scale simulations, tens of thousands of those, to be able to learn not the equations that we know, but those additional extra terms beyond that, which is the physics. So this is where we are right now, and I hope that I convinced you that I'm not a believer of deep AI learning, that you just write an enormous algorithm, you throw everything in the pixels and somehow you wait for the answer. The way that we consider AI machine learning in physics is something that requires some guidance and some knowledge to allow us to do things more efficient than what it would be, but a feedback between what the human intelligence can provide and all our knowledge that we have and what machine intelligence can provide. And I will close with what I think describes what I will just tell you, which is around
Thank you. Any
And we tried starting with a low precipitation and doubling the resolution and doubling it again and doubling it again and finding the coefficients and make a fit to see what happens when you improve the grains, right? Make them smaller, so that you have an ideal situation.
That's why I don't like to get those, because we always say the same next thing. You're absolutely right. So the thing that this is online, I shouldn't